Well, my captors have implanted some kind of module in my brain, which means I can't quite remember, but I think this is the fifth film about mole calculations. We're heading towards the sixth and final one, which is about reacting mass calculations. This one is a kind of prelude to that, and it deals with how we can use balanced equations to find out about the amount of moles in chemical reactions, or the proportions, in other words, in which they react. So hopefully by the end of this film, you'll be able to look at a balanced equation and to figure out a mole ratio from it. Quite simple. It's going to be a very short film, this one. Okay, so let's have a look at a couple of balanced equations and see if we can find out some mole ratios. Right, here are a couple. Both happen to be hydrocarbons burning, okay, but it doesn't really matter. This one's got some numbers underneath it which are just showing that it's balanced. Okay, so hopefully you've practiced balancing equations and you know that we can see, right, there's one carbon here and one carbon here, so they balance. There's 4 oxygens on this side and 2 there and 2 there, so 4 oxygens on that side, so blah, blah, blah. Anyway, what this balanced equation is telling me is that if I have 1 mole of methane, I'll be able to produce 1 mole of carbon dioxide, so long as I use 2 moles of oxygen. And in that case, I'll also produce 2 moles of water. So these numbers, or the stoichiometric ratio, or the stoichiometric coefficients is what we call these numbers, but it's not really all that important that you know that at this stage. They tell us something about the mole ratio in an equation. So if I gave you 20 moles of methane, okay, you'd be able to tell me, well, you need twice as many, because there's 1 here and 2 there, twice as many moles of oxygen, and that you'd be able to produce 20 moles of carbon dioxide. If I gave you 0.1 of a mole of methane, you should be able to tell me, well, you'd make twice as many moles of water, so 0.2 moles of water. Okay? Just to use this slightly more complicated equation here, to give you some other mole ratios, here we're told that 2 moles of gasoline, octane, this isn't octane's formula, but anyway, react with 25 moles of oxygen to produce, see, this should be 18 here, which is why this equation is not balancing. But anyway, 25 moles of oxygen, 16 moles of carbon dioxide are produced, and 18 moles of water are produced. So if I said to you, you've got 2 moles of gasoline, you'd produce 18 moles of water. That means that the number of moles of water is 18 over 2 times as great as the number of moles of gasoline. Remember, why am I using this symbol here? Because the little n means the number of moles of something. So if we read this out in words, it might look a bit unpleasant, but if we read it out in words, it says the number of moles of water, which is 18, is 18 over 2 times as big as the number of moles of gasoline, which is 2. Okay? If you're not sure about how to put these numbers up, which is basically the only reason people get confused, I could, let's say, the number of moles of oxygen is somehow related to the number of moles of carbon dioxide. People often just basically put the 16 and the 25 the wrong way up. But it should be quite a straightforward thing. The number of moles of oxygen is 25. The number of moles of carbon dioxide is 16. So the number of moles of oxygen is bigger than the number of moles of carbon dioxide. So in other words, I've got to have these things the way up that gives me a bigger number. Okay? If I wrote the number of moles of oxygen is 16 over 25 times as big as the number of moles of carbon dioxide, then that would mean that the number of moles of oxygen would be smaller than the number of moles of carbon dioxide. And that wouldn't make sense because it's 25 to 16. Okay? What you really need to be able to do is to use these mole ratios when it comes to reacting mass calculations. Okay? And as I think I said at the end of the last film, this is really the last thing that we're going to do in the Christmas term in Year 11. So if you can nail these calculations, then you've got a good chance of doing well on the calculations in the test. Last film to watch is called Reacting Mass Calculations. It relies on you knowing everything that's gone before, so everything in these previous 5 films. Can I suggest that if you're hoping to do reacting mass calculations, it would be good if you've really got quite a good sound knowledge of what's gone before. So practice the other things before you try and do reacting mass calculations.